let's take a look at Euclid's fifth postulate. And I think you'll see the reason that we're setting it aside from the other four immediately upon me reading it. So let's get straight to it. That if a straight line falling on two straight lines makes the interior angles on the same side less than two right angles, the two straight lines, if produced indefinitely, meet on that side which are the angles less than the two right angles. That's quite a bit, isn't it? Especially considering our first four postulates were just that we had lines and we could make circles and right angles are equal. Now we have word salad. Let's see if we can get through this word salad a little bit with some diagrams. Consider for a moment that we have two lines, all right? Now, if we have a third line falling upon those two other lines, then we create some angles. So let's call this point here A, this point here B, where these two intersect. We'll call this point C, and for now we'll call this point D. So if angle ABC, this angle here, added to angle BCD, if those two things totaled together are less than two right angles, then the two lines shall meet. And actually, given the drawing I've just given you here, we can see actually that yes, these two lines will meet, all right, somewhere. And they will meet on the side where the two angles do not total up to 180 degrees. All right. There's something very interesting about this postulate, and that is that for centuries people tried to prove it given the first four other postulates. It was later shown that it was impossible to prove the fifth postulate from the other four. The other thing about this postulate is what happens when you assume it is not true, or what happens when you disregard it or change it a little bit. All right. The fifth postulate is tied very closely to the idea of parallel lines and what it means for lines to be parallel. So, for review, if we have two lines AB and CD, how would you show that these two lines were parallel? With our notation, we could say that AB is parallel, with this notation here, parallel to CD. But the question always arose, well, how do we show that two lines are parallel, or how do we show that they're not parallel? How do we show that this, taken out to infinity, doesn't meet somewhere over here? It was a point of contention for a long time, and disregarding it is actually what transitions us from being able to talk about what we're studying right now, which is Euclidean geometry. And changing this postulate just a little bit, changing this assumption, allows us to instead talk about other types of geometries, such as hyperbolic geometry or spherical geometry. Okay? So there's a tie between this postulate and Euclidean geometry. Euclid avoids using the fifth postulate for quite a while in his propositions he gives forth, and we're going to avoid using it ourselves. He only uses it when absolutely necessary, and it is necessary in order to show our objective, which is a squared plus b squared equals c squared, to show the Pythagorean theorem. So we are going to eventually need to use this fifth postulate. Okay? Thank you.